Later on, the kinetic energy is 100 joules. What is the potential energy?
0.
And then later on, my kinetic is 120 joules. What is my potential? There's absolutely nothing wrong with negative potential energy. Negative kinetic energy is an issue. Because the only way you get, because the formula 1/2 mv squared is pretty much set. So the only way you get a negative is if the speed is imaginary or the mass is negative, which definitely doesn't happen in classical physics. All right, this next little exercise, I'm going to start with a little preamble. When I was doing consulting, we went to what they called boot camp, and we were all busily coding, and at some point, these people walked in, they said, all right, everybody up. And I was not the only one, but looked at them strangely. And then the tone of voice changed, and they said, we're serious, get up now. We all got up, said, all right, jumping jacks. So we did jumping jacks. So I'm telling you right now, and I am serious, I'm about to ask you, what is the formula for kinetic energy? In unison, all of you, I want you to reply 1/2 mv squared. So here we go. What is the formula for kinetic energy?
1/2 mv squared.
That was nice. Like a chorus of angels. That question will be asked at various points throughout this course and probably the next one. And matter of fact, 30 years from now, if I run into you and we first try to figure out how we know each other and we eventually get it down to here, I should be able to ask you, what's the formula for kinetic energy? And you should still know 1/2 mv squared. Why? Why is that the one that I expect you to know 30 years from now? Almost all of the formulas that we deal with in this course, it turns out at some point it starts to break down a little bit. F equals ma there's a more fundamental equation than F equals ma. F equals ma is a specific case. Kinetic energy though, 1/2 mv squared, if you're working on your Nobel Prize winning work in physics, that's the formula for kinetic energy. That formula does not change. Quite possibly is the only formula in physics that does not change when you start getting into the really the nitpicky minutia stuff. If I ask you what's the formula for potential energy, the proper response is which one? Let's just try that one out. What's the formula for potential energy?
Which one?
There we go. So that implies there's more than one. So first I'm going to just present the formulas to you for potential energy, and then we'll actually derive one of them. Questions before I continue erasing? You know, you say something controversial and people just go storming out. All right, so the conservative force its weight, the potential energy formula, actually that's the one we're going to drive, we're going to leave that one blank. The generalized gravitational force, negative big G, mass 1, mass 2 over R. The elastic force, 1/2 K delta X squared. I think those are the only ones I wrote. I guess it's on the previous page. We'll do electric. K sub C So as we analyze problems, we're gonna do the force diagram, just like before, figure out which ones are doing work. If any of those conservative forces are doing work, we'll use one of the potential energy formulas. Questions here before we derive that first one that I left blank?
Is that parentheses around the displacement and last two forces?
It is a parentheses around the delta x. I keep putting it down. There it is. Need to stop putting it down on the black notebook. All right. I know that the conservative work is equal to, something I hadn't arrived at, is equal to the conservative force times the displacement. There's one other thing that I did jump over. So, jumping back just a little bit. I know that the total work is equal to the change in energy. Total work means all of the work. I have only two types. I have conservative and non-conservative. So this is conservative work plus non-conservative work. That's my total. Is equal to the change in energy. Well, I have only two types of energy I'm dealing with here, kinetic and potential. So that's equal to the change in kinetic plus the change in potential energies. I know that, let's try that one again. Total work is equal to the change in kinetic energy. There we go. Mistake there. I know non-conservative work is equal to the change in energy. So conservative work plus the change in total energy is equal to the change in kinetic. I'm going to isolate the the conservative work. So that's equal to the change in kinetic energy minus the change in energy. My energy, I just have two types here. So that is the change in kinetic minus the change in kinetic plus change in potential energy. Distributing, so I have negative K minus delta K minus delta K minus delta U. The delta K's cancel out, and I'm left with conservative work is equal to the negative change in potential energy. So we have our three work energy relationships. We have the total work is equal to the change in kinetic energy. We have the non-conservative work is equal to the change in energy, and the conservative work is equal to the negative change in potential energy. Those are the three work energy relationships. So now, back over here. The conservative work is the conservative force times displacement, and that's going to be equal to the negative change in potential energy. I'm going to deal specifically with the scenario of an object near the surface of the Earth falling, or near the surface of some planet falling. So, object falling. Let's do force diagram. What are all forces acting on the object?
Wait.
And then, just for completeness, throw a weight down there. All right, that's it. Is this a conservative force?
Yes.
Yeah, it's the only one we've dealt with so far that is on the list. So in this particular case, the conservative work is going to be the weight downwards. Probably should establish a sign or something. It doesn't matter if up or down is positive. All right, we'll make down positive. So weight dot the displacement. So let's say it starts at some initial height and it goes to some final height. So it's just gonna fall that far. That's gonna be equal to the negative, well, change in U, what is change? Yep, so that's U final minus U initial. My weight is mg. It's in the same direction as the following. So this distance right here, hi minus hf. Hi is bigger than hf, so I know that my work is positive. If we had chosen up to be negative, the work is still positive, because the work is in the same direction of movement, and so the dot product would be positive. That's equal to negative U final plus U initial. Distributing over here, I have mgh initial minus mgh final is equal to U initial minus U final. So the question is, what is a formula for U that would satisfy this equation?
U equals mga.
Yeah, that would work. So if U equals mgh, then U initial minus U final would be mgh initial minus mgh final. It works. What is another equation that would also work? I would tell you, there are an infinite number of solutions here. I'm just looking for one more. And I think this falls into the category of something so obvious people don't think about it. Why don't we do a couple numbers here? Let's make a mass of 5 kilograms. This distance right here will make 10, no, I'll use 10 for something else. Let's make it 4 meters and put it on Earth 2, so G is 10 meters per second squared. So what would be mgh initial minus mgh final? Perhaps it would help if, all right, let's come up with some more numbers here. Why don't we make this distance from the ground to here 6 meters, and this distance right here 2 meters. What is mgh initial?
6. No.
The mgh initial. Okay, so this would be 300 joules. What about mgh final? 100. All right. So what is ui minus uf?
200 joules.
Yeah, so that'd be 200 joules. What else could we have subtracted to get 200? Besides 300 minus 100, there are other solutions for that. It's not a trick question. I told you something so obvious that people don't think about it. Give me something else. Give me 2 other numbers that I can subtract to get 200.
500 minus 300.
So
400, 200.
400 and 200. So what's the difference between 400 and 200 and 300 and 100? right, let's do one more pair.
500 and 300.
All right, and what's the difference between 500, 300, and 300, 100?
200.
Yeah. So we get the exact same difference, all we have to do is just add some number to it. So the potential energy formula, the general potential energy formula would be mgh plus some constant. That plus c there is just a constant. I can add a constant to, as long as I do it to both of them, that constant's going to cancel out. But that constant gives us a nice little freedom in the fact that I could have also done 200 and 0. I could have made 0 equal to here. I could have made that, my potential energy is equal to 0 at that point, and then all I have to care about is the 400. There's nothing special about the ground here, other than it's a nice reference, but I do less math if I make one of my potential energies 0. So whenever you're doing a potential energy problem, unless it is given to you, it is often helpful just to establish this is where I'm going to make potential energy equal to 0.
So we could have just done 5 times 10 times the 4. So why did we do the 6 and the 2? Just to...
Well, people were being silent, so I thought that they were struggling with the fact that what exactly is H initial and H final. I was going to eventually get around to, I could have made H equal to 0 wherever I want.
In my head, the H final was, I used the 4.
Yeah.
And I got 200 as well.
Yeah.
Okay,
Yeah, that's absolutely, that's the quickest way of doing it. There's a problem that I gave years ago. It was a 152, 252, 152, I think I did for both, where I gave a surface of a charged sphere and I said, how can the potential energy at the surface equal 0 joules? And the answer was, because you can set 0 anywhere you want. Unfortunately, no one got the question right. They were jumping through hoops trying to figure out how to calculate to get 0, but it's as simple as you make 0 wherever you want. Let's just do a quick and dirty problem here. So I've got the mass here. We'll make it a 5 kilogram mass. It is going to fall, oh, what the heck, 4 meters. Put the ground down here. We'll make that 2 meters. This might look familiar. We've established the only force acting on it is conservative force, so energy is conserved. So if I start with this right here, we'll skip a number of these steps at some point, but for right now, we're going to start with the middle energy relationship. The work non-conservative is equal to the energy final minus the energy initial. As it falls, what is the non-conservative work being done?
0.
Yep. So 0 equals E final minus E initial. In other words, if I add that over here, my initial total energy is equal to my final total energy. Once we establish energy is conserved, that we can get right to there. I have 2 types of energy. Rest energy only comes into play if the thing spontaneously combusts on the way. We're not dealing with spontaneous combustion. What are the 2 types of energy?
Potential and kinetic.
So I have kinetic initial plus potential initial is equal to kinetic final plus potential final. Let's have it start at rest. The initial speed is 0 meters per second. So let's go ahead and do the formulas here. What's the formula for kinetic energy?
1/2 mv squared.
Wow, it sounded like a single voice. That was so impressive.
Ask us again.
What's the formula for kinetic energy?
1/2 mv squared.
Like the Riverdance of responses. 1/2 mv initial squared, and over here we'll have a 1/2 mv final squared. All right, let's see who remembers. What's the formula for potential energy?
Which one?
Thank you. The one associated with weight.
mgh plus c.
Yeah, so I'll just put down the mgh part, because I can put plus c and plus c, but they'll cancel out. mgh initial, and over here plus mgh final. Now, as you get more comfortable with this, you can skip a number of these steps, but for now, I'm not gonna skip the steps. All right, so I've got my 4 terms here. Which of these are equal to 0? MGHI?
Yeah.
Why? Because what?
Doesn't have like this square thing.
There's no square thing here.
Yeah.
Half would be 1/2. 1 mgi squared.
You're saying that's 0? Why?
Because velocity initial is 0.
Or specifically speed.
Speed.
We're dealing with scalars. All right, so that's 0 because the initial speed is 0. You said,
I tried, please, never mind.
okay. Anything else equal to 0?